Good morning, madam. Can you hear me?
Yes, I can hear you. Can you hear me?
Yes, madam.
Okay.
Just wait. Madam, we will wait for 5 more minutes so that the participants can join.
Sure, that's fine.
Thank you. Good morning, everyone. Good morning, everyone. I welcome everyone to this third day of 1 week online National FDP on fundamental mathematics. This program basically celebrates birth anniversary of Mariam Mirza Khani, the only woman field medalist till today. A quote by Mariam Mirza Khani: I don't think that everyone should become a mathematician, but I do believe that many students don't give mathematics a real chance. I did poorly in math for a couple of years in middle school. I was just not interested in thinking about it. I can see that without being excited, mathematics can look pointless and cold. The beauty of mathematics only shows itself to more patient followers. Once again, good morning to everyone. Now I call upon Nikita to introduce today's speaker, Nikita Agarwal madam.
Thank you, ma'am. Good morning, everyone. I, G. Nikita, faculty member of Mathematics and Statistics Department, RBVRR Women's College, welcome you all once again to day 3 of 1 week National Level Faculty Development Program organized by Mathematics and Statistics Department, RBVRR Women's College. I take this opportunity to introduce our speaker of this session, Dr. Nikita Agarwal, Associate Professor of Mathematics at Indian Institute of Science, Education and Research, Bhopal. Her research interests lie in pure and applied dynamical systems. Dr. Agarwal received her bachelor's degree in mathematics from Lady Shri Ram College, University of Delhi, and her MS and PhD degrees from the University of Houston, Texas, US. She is a member of the Executive Committee of Indian Women and Mathematics. She is very involved in outreach programs. For example, she is an active organizer of birth anniversary celebrations of Mariam Mirza Khani in India. She has 3 single publications and several joint publications. Now I invite Dr. Nikita Agarwal, ma'am, to take over the session.
Thank you very much, Nikita. And I also would like to thank the organizers for inviting me to give a talk here, and especially Dr. Shweta and Dr. Uma. So I hope I'm audible to all of you.
Yes, ma'am.
Yes, madam, you are audible.
Okay, very good. So I will share my screen and take it forward from there. Can you see my screen?
Yes, madam.
Okay, good.
You can see.
So, okay. So I'm going to take this opportunity to talk about life and works of Mariam Mirza Khani. And now I think she does not need any introduction. This program has been running for several years now, but I will talk about it. I will talk about her life, which not everyone may be aware of. And I'm sure there will be several places where you will feel inspired. You will feel that nothing can be a roadblock if you want to pursue something. So you will see how even with all the challenges she had in the later part of her life, in terms of health issues, she still continued to do wonderful mathematics, and even today there are works all over the world that are inspired by her works. So so let me begin with this picture, and I hope you're aware of the fact that Mariam won 2014 Fields Medal, and she is the only woman mathematician to have won this medal since the inception of the award. And International Mathematics Union, IMU, um, uh, has written the following about the award that she got. So Mariam Mirza Khani is awarded the Fields Medal for her outstanding contributions to the dynamics and geometry of Riemann surfaces and their moduli spaces. So in this talk, it would be very difficult for me to touch each and every aspect of her work, but I would try to, for the audience that I'm aware of, I'll try to give a glimpse, give an idea of what this area is and what kind of problems she handled and what is the impact of those problems. Okay, so I'm going to pick a few of the problems that she has solved along with her co-authors. So this picture is of the four 2014 Fields medalists, and Maria Mirza Khani is to your right. Okay, and before I begin talking about her research, let me talk about the awards that are under her name, and also about her journey, academic journey, before she became this world-renowned mathematician. So she has several awards to her credit. She got American Mathematical Society Blumenthal Award in 2009. She has also visited India at the International Congress of Mathematicians, which was at Hyderabad. And she gave an invited talk there in 2010. I'm not going to talk about all of these, but some interesting ones. She is named one of the Nature magazine's 10 people who mattered of 2014. Okay, not just mathematicians, people who mattered. She was elected foreign associate to the French Academy of Sciences in 2015. She is also an elected fellow of American Philosophical Society, National Academy of Sciences, American Academy of Arts and Sciences. And the last one is really interesting, that there is an asteroid which is named in her memory. Okay? And about her childhood, in the introduction started with a quote of Mariam, right? That not everyone has to do mathematics and various other things. So this is very much in line with that. So she was born on May 12, 1977 in Iran, and her childhood was spent in Tehran during the Iran-Iraq war. So those were difficult times when she was she was a child. She did not do well in mathematics in her first year at her middle school. And by then teacher, she was told that she did not have mathematical talent. Okay. And at that time, she thought that she would be an author, because she was really interested in reading novels, reading books, and also writing. But there was a change in teacher who saw Mariam flourish mathematically. So it's not something that one is not aware of, that teachers play a very important role in where we are in life, right? What we end up doing. They inspire us, they open doors for us. And I think it's a responsibility of every teacher to give that helping hand and to give that kind of support and guidance to their students who are generally interested in doing something. Okay, so there's this teacher who thought that Mariam had something and she would flourish mathematically. Okay, so and then there was no looking back for Mariam. So she has been the gold medalist of Olympiad. Mariam and Roya Beheshti. So Roya Beheshti is her lifelong friend. They broke into what was once considered a boys only bastion. So going to Olympiads and winning Olympiads, that was considered a boys thing at that time. And they broke this thing, and they were selected to represent Iran in the International Mathematical Olympiad. Mariam won a gold medal in 1994, which was held in Hong Kong, and she got a 41 score out of 42. And 1 year later in Toronto, Canada, she won a gold medal again, but she got a perfect score. And there's also this story that she says that it was an easy paper and that is why she scored a perfect score. So she was that modest. So this is a picture on the left of Mariam with her classmates. And on the right, there's this picture, on your right, there's the picture of Mariam with her friend Roya. Okay. So about her early education, it was in Iran. So Bachelor of Science at Sharif University of Technology in Tehran during 95 to 99. And by this time, during her bachelor's, she had already published 3 papers, of which 2 were in graph theory. Okay. And one of the papers actually is just solving a problem that was posed by her teacher. And it was a conjecture at that time, and she solved that conjecture. And she always enjoyed problem solving and participating in informal reading groups with peers. And I will just give you I'll just talk about this excerpt of a professor at Toronto and also Mariam's friend. So I'll not go over all of what they said, but let me just talk about what is underlined. So she was asked to referee somebody else's grant proposal when she was an undergrad. So she was already considered to be so mathematically intelligent that she would be asked to referee somebody's or give comments on somebody else's grant proposals, research grant proposals, when she was an undergraduate student. And on the other hand, when not about academics, but she would play a lot of soccer, and Mariam always said she wants to come play. The only girl who actually ever did. So she was interested in not just academics, but also sports. Okay. So this is also something something to take from. So academics alone, so along with academics, one should also have other interests to pursue, because mathematics especially is such a subject where you need constant focus. You're not working in labs, for example, you're working in your room with pen and paper, and you can't be doing mathematics for 24 hours with no breaks. So you need to have a fresh mind in between, and you need to have other interests. It could be music, it could be sports, it could be reading, it could be anything, but something which is refreshing, which can, take your mind off the stress that is during, sitting alone and doing something. So it's very important. Now, about her doctorate, she got her PhD from Harvard University in 2004. Her doctoral advisor is Curtis Macmillan, who is also a Fields medalist, and he won the Fields Medal in 1998. Her thesis was 130 pages long, and it was titled Simple Geodesics on Hyperbolic Surfaces and Volume of the Moduli Space of Curves. For her thesis, this Leonard and Eleanor Blumenthal Award. Okay? And it was just an outstanding thesis. And she worked, so the work that she did during her PhD was published in top journals such as the Journal of American Math Society, Inventiones Mathematica, and Annals of Mathematics. Okay, and this is what her advisor has to say, that she had a sort of daring imagination. She would formulate in her mind an imaginary picture of what must be going on. And then she would come to his office and discuss things. So she was very creative in that sense. I hope I'm audible. I hope I'm audible. I hope I'm audible to.
Yes, ma'am.
Okay, thanks. Okay. Now, about her career, she got assistant professorship at Princeton University in 2004, and she got professorship at Stanford University. Sorry, are you saying something? Okay. So she became a professor at the Stanford University in 2009, and as per MathSciNet, she has published a total of 23 papers in the short duration, and her work has been
Excuse me, madam.
cited. Yes.
Dear participants, all of you mute yourself. All the participants, I'm requesting that you have to mute yourself. Yes, madam, you can continue.
Okay. So Mariam has published a total of 23 papers in her short academic tenure, and her work has been heavily cited. So this number I got yesterday, and her work has been cited 713 times already. And there are also 21 papers that are related to her. So though the ideas and imagination in her work cannot be measured through the number of papers. Okay? So let me now talk about her work and legacy. So she worked in an area which is broadly known as hyperbolic geometry. So let me introduce you to this area first. So on the left, you see these three surfaces, right? So the surface in the middle is like a cylinder, and this is called a flat surface. Okay, because if you take any point on the surface and you take a local picture, you look around, it's like a flat piece. Okay, now so there is no curvature. Whereas if you look at the front picture, it's known as a hyperbolic surface, and at every point you see a saddle. Okay, so you know what a saddle is. And the picture on the back is a spherical surface, right? It's like a sphere. And what is interesting is how triangles look like in these surfaces. So first of all, let me describe what a geodesic is. So a geodesic is a line of shortest path between 2 points in any space. Okay, so this is the picture that you see, which is the same as the front picture here. Okay, now if I take 3 points on this surface, let us join these 2 points. Okay, now the shortest path between these 2 points is a piece of hyperbola on this surface. Similarly, this is a piece of hyperbola and this is a piece of hyperbola. So when you look at this triangle, its 3 edges are not straight lines, but they are pieces of hyperbola like this. So if you add all the interior angles of this triangle, it's less than 180 degrees. Okay. So this is how you see these three surfaces. So on the flat surface, the sum of interior angles of a triangle is 180 degree, is actually equal to 180 degree. On hyperbolic, it's less than 180, and on spherical, it's greater than 180. Okay. Now this was one of the postulates of Euclid, right? That sum of angles of a triangle is interior angles of a triangle is 180 degree, but that was for Euclidean geometry. Now we are going away from Euclidean geometry, where the sum of interior angles is actually less than 180, like in this surface. Now, Mariam has made novel contributions to several areas of mathematics, including algebraic topology, geometry, and ergodic theory. And her main research theme is to understand the geometry and dynamics on hyperbolic surfaces, such surfaces. Okay? And hyperbolic geometry is found in nature, and it has also inspired several artists such as Escher. Now, in coral reefs, you see such saddles, okay, such hyperbolic surfaces having what is called, so let me go back. So I forgot to talk about the signs. So under hyperbolic, you see a negative sign, flat you see 0, spherical you see plus. So these are curvature. So on flat surface, curvature is 0. On hyperbolic surface, curvature is negative, and spherical curvature is positive. So we are in the negative curvature regime. Okay, so now the second picture is called Circle Limit 3 by Escher. This is a sodalite from a chemical compound. And the last one are lettuce leaves, right? They also have this hyperbolic geometry. Okay. So now let me come to talking about three of her works. Okay. So the first work is about counting simple closed geodesics on a hyperbolic surface. So let me take a very simple example of two torus. Okay. So what is two torus? You take two donuts. So one donut is called a torus. You take two torus and join them. So you can imagine there are two vadas which are joined together. So this is the first vada and this is the second vada, and they are joined together. Okay. So that's my surface. Now I am looking at two curves, two types of curves on this, the blue ones and red ones. So let us first look at the blue one. So this blue one, you can imagine looking at one of the holes of the vadas and taking the boundary like this. Then this one is the middle curve that is on the joining of two vadas. And again, like this one, the dotted one means it's at the back. Okay, the portion of the curve on the back. Then there is this red curve. Now, red curve is a long curve, but it's interesting. And what is interesting about it is the following. First of all, let us see what the red curve is. So the solid one is on the front. Okay, so let us start from here. So you are on the top. Then from this you go the back. Then you again come to the front, go and come to the front, go at the back, front, back, and you back to the point where you started off with. Okay. So now what is interesting about all these four curves is they don't intersect themselves, right? So red curves and all blue curves are simple and closed. Closed means the initial point and starting point is the same, and simple means they don't intersect themselves. Okay. So now Delarte and their co-authors, they proved what is known as prime number theorem on a hyperbolic surface. and they prove the following, that the number of closed curves, I'm not talking about simple. When I say closed, they mean closed and they can intersect themselves also. Okay. So the number of closed curves of length at most L is asymptotic to e to the power L divided by L. So you remember the prime number theorem, right? So the number of primes less than or equal to x is e to the x by x asymptotically, right? So this is like prime number theorem, but now for closed curves on hyperbolic surfaces. Okay, so they follow like a prime number theorem. So when I say asymptotic, that means as L becomes very large, as length becomes very large, the number becomes like e to the L by L. Now, Marja Mirzakhani proved something more, which is when you have a hyperbolic surface of genus G. Now, what is genus? Genus is the number of holes. So here there are 2 holes. You can also imagine having 3 donuts joined together with having 3 holes and so on. So you imagine a hyperbolic surface of genus G. G means the number of holes. That the number of simple closed curves. Now she's not just talking about closed curves. She's talking about simple curves also. That means they don't intersect with each other. And the number of them of length at most L is asymptotic to a constant times the length to the power 6g minus 6. So what is 6g minus 6? It's g is the number of holes, right? So for example, from this picture, g would be 2. So this power would be 6, right? 6 times 2 is 12. 12 minus 6 is 6. So that's what she proved, where the constant is depending on the space x in a very nice way. Okay, so it only depends on the surface x. Now, what is interesting to note here is the following. So when you look at the number of closed curves, that's exponential, whereas the number of simple closed curves is only polynomial, right? That means that when you look at simple closed curves among all the possible closed curves on a surface, it's rare, right? Because on one hand, closed curves are exponential and simple closed curves are only linear. I'm sorry, this polynomial factor, right? So this is something remarkable that she proved. Now the second problem is what is known as another proof of a conjecture by Witten. So Mariam gave another proof. There are, of course, this conjecture was already solved. There was a proof already, which was given by Kontsevich in 1992, and for which he was awarded the Fields Medal in 1998. So Mariam also obtained. So while proving this conjecture, she also obtained several asymptotic formulas, one of which was to compute the frequencies of different types of simple closed curves. I'll talk about one specific thing here. So to talk about the second point specifically, let us look at this picture. Now this picture is very much like the previous picture. It's 2 donuts joined together. This green curve, there are 2 green curves, right? There is this blue curve and there is this red curve. The red curve is different from the other 3 curves. In what way? So if I cut along this green curve, any of the green curves, I just get one single surface, right? So imagine that these donuts are, or these vadas are hollow, okay? So when you cut along this green curve, you will get one single piece, right? Similarly, when you cut along the this blue curve, again you will get one piece. Whereas if I cut along this red curve, then I get 2 vadas, right? So this red curve is what is known as a separating curve, meaning if you cut along that curve, your surface splits. Whereas there are called non-separating curves, which are these green and blue curves, where on which when you cut, you still get one single surface. It's not a donut, it's not a union of donuts any longer, but it's a single surface. So what she proved was on genus 2 surface, which is a surface like this, a sufficiently long, simple closed geodesic is 6 times more likely to be non-separating than separating. What does it mean? So if I look at a simple close, so simple, you know, meaning it does not intersect with itself. Closed means it closes up. Geodesic means it's a curve of shortest length. Okay. And if you put all of this together, then the number of separating, so if you look at the fraction of separating to non-separating, it's like 6:1, right? So you have 6 times more separating curves like, more likely to be non-separating. So there are more curves like green and blue curves, 6 times more than these red curves which separate the surface. Okay. So this is another, so she proved this conjecture, but along with proving the conjecture, she got several other results. Now, finally, let me talk about one of the most talked about results of hers, which is known as magic wand theorem. So in a massive article with over 200 pages, Eskin and Mirzakhani, and later with Amir Mohammadi, they proved the famously known magic wand theorem. It led to the resolution of various unsolved mathematical problems, and an application of this result is to a mathematical problem known as the Illumination Problem, which was posed in 1950s by Strauss. So it's very easy to state the problem. So let me state the problem first. So you are all sitting in a room. So imagine that rooms in your wall are all mirrored. Okay, so there's mirror on the walls. Now, as the light ray hits the wall, it reflects back at the same angle as the angle of incidence. Okay, so this is something that you have read in physics. So angle of incidence is same as angle of reflection. Now, if a candle is placed at some location in the room, will it illuminate every other point in the room? Okay, so the question is, if I place a candle or a light source at some location in the room, will every point in the room get the light or get illuminated? Okay, mathematically, what does it mean? It means that if I start from the light source, from the candle, there are sequence of lines, okay, which take me to every other point in the room. So by sequence of lines, I mean this light source will throw a straight line to the mirrored wall. Now, at whatever angle it goes there, it will get reflected back. It will go somewhere else to another wall, again get reflected back. So it will keep on reflecting back and forth. So is there such a path which takes you to any other point in the room? That's the question. Okay. So there are these two examples of 26-sided polygonal room and 24-sided polygonal room by Tokarsky. So left one is by Tokarsky and right one is by Castro, where in these examples, what happens is, imagine all the sides are mirrored, okay? And they are following the same principle. And you see, let us look at the left picture. There are two black dots, right? So what Tokarsky proved was that if I have a light source on one of the black dots, then it will illuminate all the points of the room except for the other black dot. So for example, if I am on the left black dot, okay, then I can reach through the sequence of straight lines to any other point in this blue region, blue room, except for the other black dot, and vice versa. Okay, so same happens if you're on the other black dot, then you can't go to the previous black dot, but you can go anywhere else. So there are 2 points in the room, right, which are not illuminated and other points are illuminated. And same happens for the picture on the right. Okay, the difference is that the first one is 26-sided polygonal room and then the next one is 24-sided. So now what Mariam's work did was to answer this question, to solve this illumination problem. Okay, so it works on general translation surfaces. I'll not go into what translation surfaces are in general, but what they proved was on translation surfaces, which is a generalization of polygons. Let me not go into that. Just let me talk about what is written here. So using Mariam Mirzakhani's work, several authors resolved the illumination problem. So she did not solve it, but her work was used heavily to solve this problem. And what they proved was the following. So if you take a polygon room, the previous 2 examples were polygon rooms. So if you take polygon rooms such that each interior angle is a rational multiple of pi. So a rational times pi, okay, each interior angle, then no matter where the candle is placed, only at most finitely many locations in the room will not be illuminated. So they can't be pockets which are not illuminated. There'll be only finitely many points in the room which possibly will not be illuminated. So what Tokarsky and Castro said was special cases of this, right? In their example, there was only 2 points, right, which were not illuminated. So, but in general, if you have a polygonal room where each interior angle is a rational multiple of pi, then no matter where the candle is placed, only finitely many locations will not be illuminated. Everything else will get illuminated. Okay, and as I said, they proved it for more general surfaces which are known as translation surfaces. Okay. Now that ends the talking about her work. Now let me come back to Mariam. So Mariam was battling with cancer since 2013, even prior to getting the Fields Medal Award in 2014. And she lost the long battle against cancer in July 2017. And she has left researchers with plenty of ideas and thoughts to build upon. Her novel contributions directly and indirectly to several areas of mathematics and physics are still unfolding. So on the right, you see a picture of Mariam where she is drawing pictures, actually surfaces on a paper. So she had a big ream of paper folded and she would draw pictures on that. Okay, so she is often called a doodler. Okay, and coming to her family, this picture on the right is with her parents, Ahmed Mirza Khani and Zahra Hagi Gigi. So that's this picture of hers while she was in college in Iran. While at Princeton, she met her husband, her now husband, John Wondra, who is a Czech national and who was a postdoctoral teaching fellow then. They married in 2015 and he is a professor of mathematics at Stanford University. And they have a daughter, Anahita, who was born in 2011. And this is a picture of them, of them, right? Okay. Now, she is widely remembered. So on the left, you see her sculpture at the National Library and Archive of the Islamic Republic of Iran in Tehran. On the right, you see a Twitter post by Iranian president when she won the Fields Medal. So congrats to Mariam Mirzakhani on becoming the first ever woman to win the Fields Medal, making us Iranians very proud. And there is a Mariam Mirzakhani Prize in Mathematics, which is given to mid-career mathematician for exceptional contributions to mathematical sciences. There's also a Mariam Mirza Khani Award by Australian Math Society to support international female students. So there is a lot of there are a lot of things that are happening around the world to remember remember and acknowledge the contributions of Mariam. Now, during the introduction, this was talked about. So May 12th is Women in Mathematics Day. So May 12 is Mariam Mirza Khani's birthday, and it's recognized to celebrate women in mathematics. Started in 2019 with more than 100 events all over the world. There were several in India as well. And today's program, or this entire program, is part of this May 12 initiative. And it's coordinated by several women organizations across the world, including Indian Women in Mathematics. And this is the website of May 12 if you're interested to have a look at it. And finally, let me talk about a few things here. So first of all, some credit to WWW for the images that I have taken. Along with Professor Ridhisha and Professor Geeta Venkatraman, is also one of the speakers in this session, in this program. So we wrote an article on Mariam Mirza Khani in Resonance, Journal of Science Education. It's freely available online. So if you want to learn more about Mariam Mirza Khani, you can go over this article. It's a short article of about 10 pages. Then there is, in 2018, in Notices of the American Math Society, there was an article on Mariam, and also an article on Mariam by Jayadev Atreya in Bhavana, which is also a mathematical magazine in 2018. So this is also freely available. You can have a look at it. And finally, to two things that are worth watching. So the first one is this movie documentary, Secrets of the Surface, the Mathematical Vision of Mariam Mirza Khani. It's a movie by Zala Films of about 50 minutes talking about Mariam. So I have also written a review on this documentary, but anyway, I would request the department if they can get hold of, if they can subscribe to this movie and have a movie screening session for your students. It's a wonderful movie talking about Mariam's, the challenges that she faced, how she overcome those, what was her journey, several interviews by her friends, family, and also academic community. And finally, something that is freely available to you. It's a short 20-minute film created by International Mathematical Union Committee for Women in Mathematics, Journeys of Women in Mathematics. It's available on Math Union website, but it's also available on YouTube. You just have to search Journeys of Women in Mathematics. It'll give you a 20-minute movie. And so Professor Neela Natraj from IIT Bombay, she features in this movie. Her mathematical journey is talked about, and so is the journey of several women mathematicians across the world. So it is quite it's inspiring for everybody, not just for women, but I would say for everybody who wants to pursue a career in mathematics or do something substantial in life, and it would be motivating to everybody, especially women. So I would encourage you to watch this movie, and I will stop here, and if there are any questions, I'll be happy.
Dear participants, if you have any questions, you can ask the madam, or otherwise you just post it in the chat box so that madam will be answering that questions.
Shweta. Shweta,
Yes, good morning, madam.
good morning. Can I say something to 1 minute?
Yes, madam.
Yes, madam, your talk is very inspirational and is motivational. I was so happy to hear about this mathematician, Markazani, really inspiring. And you gave so much of information about women in mathematics.
Madam, we can't hear you.
Oh, sorry. Now, can you hear me?
Yes, madam.
Yeah, madam's lecture is very motivational and inspirational. Can you hear?
Yes, we can. I can hear you.
Yeah, I was happy to know about this mathematician, Markazani. Yeah, I didn't know till now. I didn't get to know about that mathematician. And also there's a website and YouTube information about women in mathematics. These things really, for mathematics lovers, and inspirational, and also for the youngsters, it is motivational. Yeah, I would love to go through those things, and I was happy to hear your lecture. That's why I'm just interfering. Yeah, even
Thank
though
you
I'm
so
very
much.
tired.
In fact, this program, this first program, and also the one that is happening towards the end of this month, they are both listed on this website. So these events are registered on the website, so the world knows that these programs are happening in Hyderabad.
Oh, really?
Right.
Yeah, it's very nice to hear that. So I would like to go through them. You motivated me also after a long time.
Happy to know this.
Yeah, even though I'm retired long time, just I felt happy and inspirational to hear these. A very short life she has, Markazani. Yeah, it's very saddened, but her contribution was really amazing to the mathematical community. So that's why I just wanted to interact, and thank you for giving such a good information. Thank you. Thank you, Sweta.
You're welcome, madam. Anyone wants to speak?
So if I don't see any questions, so I will just make one comment regarding this is also something that I truly believe in, and also it is very clear from Mariam's contributions, academic contributions. So one is that you see, she worked in an area which is at the interface of several areas, right? In mathematics, we think of few broad areas, right? Analysis, algebra, topology. Then number theory has now branches, analysis, algebra, so it can fit in those areas. Then probability is considered an analysis subject. So I will just say analysis, algebra, topology, keeping in mind that there are branches. So as a student, you might feel that why should I learn all these subjects? What is the need of learning all these subjects? I am good in analysis. I will just keep on doing analysis, even at MSc level, even at PhD level. And I'm sure your teachers will agree with me that at research level, it doesn't work like that. One has to really have some basic knowledge or interest or inclination to learn anything that is demanded by your problem. Okay, so one has to know everything basically. Not really advanced. I mean, I don't know all of, I'm an analyst broadly, but I don't know all of analysis. I don't know a lot of algebra. I don't know a lot of topology, but with my background, having a bachelor's degree, having a master's degree, having a PhD in mathematics, my training is such that I can pick up a book and learn it on my own. Okay. And I have that open mind to learn something new, which is beyond my comfort zone. Okay. So at this point, you should not doubt that, why is this subject there in the curriculum? I am sure if you compare your curriculum with other curriculums, they are sort of right. There is a reason why a topic is there in bachelor's curriculum, because understanding of various things, so that when you pursue your own mathematical career, it's very easy for you to pick up things. Okay, so diversity in areas, having an open mind in learning is very important, not just in mathematics, but I would say in any discipline, you should keep an open mind. Okay, so that's what I wanted to say. And Mariam's area is quite at the interface of several areas, right? Yeah. That's all I had to say.
I thank you, madam, from the bottom of my heart for taking time from your busy schedule to be the speaker for this National FDP. Your presence and wise words help magnify our cause in the best possible way. All thanks to your enlightening words that inspired so many people out here, so many participants. They have your speech has been enlightened, madam. Your lecture has been enlightened so many participants today. Thank you. And now I call upon Nikita to propose formal vote of thanks. Nikita?
Yeah, thank you, ma'am. It is my pleasure to present vote of thanks on behalf of Department of Mathematics and Statistics, RBVRR Women's College. At the outset, I thank our today's resource person, Dr. Nikita Agarwal, for accepting our invitation. And ma'am, we are all inspired and motivated by the Mariam Mirza Khan's life, work, and legacy, especially counting the simple closed curves, another proof of conjecture by within, magic wand theorem, translation surfaces, awards and honors, especially Fields Medal. Also thanking you, ma'am, for this wonderful lecture. We are all enlightened with your knowledge. And also, ma'am, we would love to watch the movie Journeys of Women in Mathematics. The day 12th May is celebrated as Women in Mathematics Day, the birthday of Mariam Mirza Khan. We are thankful to our Honorable Secretary, Hyderabad Mahila Vidya Sangam, Professor K. Mutyam Reddy Sir, and our Secretary cum Correspondent, RBVRR Women's College, Professor G. Sudarshan Reddy Sir, for their continuous encouragement in organizing program. I would like to thank our principal, Dr. J. Achita Devi, for her support. A special thanks to Sweta Srivastava ma'am for organizing this 1-week National Faculty Development Program. Our heartfelt thanks to all the participants. Thank you, ma'am. And also thanks to the Dr. Nikita Agarwal ma'am for accepting our request. Thank you, ma'am.
Thank you, Nikita.
Thank you, Nikita.
Madam,
Thank you, ma'am.
there's a small appreciation certificate for you, madam. Please accept
Thank
it.
you. Thank you, ma'am.
Welcome, ma'am. I just sent this appreciation certificate to your mail, madam.
Sure.
Thank you, madam, for readily accepting our invite in spite of your busy schedule.
Thank you very much. It's my pleasure, and I'm sure it will be a wonderful session with great speakers that you have on this.
Thank you, madam. Dear participants, now we will be rejoining for the next session at 3 o'clock today on the graphs constructed from algebraic structures and the different kind of spectra by Professor Pratima Panigrahi madam at 3 o'clock.
Shweta.
Yes,
Shweta.
Yes.
సర్టిఫికెట్ లో హిజ్ అని ఉంది అక్కడ మేడం సర్టిఫికెట్ లో హర్ అని ఉండాలి చేంజ్ చేసి పంపియండి
ఓకే ఓకే
ఓకే
we will again rejoin at 3 o'clock. For the next session. Thank you all.